Hey everyone, problem set 1.6 video key here. How exciting, I know. Piecewise functions. All right, so a piecewise function, as is defined here, I'll kind of explain this in different words, let you read that yourself. But basically, we're going to have like kind of two different pieces to a graph. We're going to have this line right here, but we're only going to graph it for these x values. And we're going to have this line right here, and so only going to be graphed for those values. These don't have to be lines, that's just what this problem happens to be, but one of them could be like a quadratic or an absolute value or any function that we've studied so far. So here's a picture where like first we had a parabola, so like a part of a quadratic, then the quadratic graph changed to a horizontal line, and then that changed to like kind of a more normal kind of line. So you can have all sorts of different pieces here. But to graph it, what we want to do is just start at the x value that's over here. It's probably the easiest way to do it. So I'm going to color code these. This will be my blue piece here. Then we'll do how about an orange piece down here. Okay, so for the blue piece, I'm going to start at x equals -1. Now, even though here we don't have an or equal to symbol, that just means I'm going to make this point a hole in the graph instead of a filled-in circle. But we're still going to start at -1. So I'm just going to plug in -1 right here and get 2 times -1 plus 1, which is -1. So our blue piece gets to start at -1, -1. As I talked about already, that's going to be a hole. Now this graph only exists for x values that are less than -1. So less than -1 is going to go, the graph's going to be like over here somewhere. The blue graph will not exist over here at all because these numbers are greater than -1 for our x values. Okay, so it's called a domain restriction, which domain just means x values. So now we can graph this one of two ways. We can either just pick another x value as long as it's less than -1, plug it in here, get a second point, and then draw it over here, and then connect the 2 points. Or we can just use the slope since it's a line. I'm going to use the slope for this one, and for the orange one, I'll just pick 2 points. So for the blue one, if our slope is 2, now I can't go up 2 over 1 because then I'll be at an x value of 0, which is bigger than -1, which we're not allowed to be bigger than -1 for the blue piece. So I can go down 2 and over 1 this way instead. So then I end up right here. If you want to, you can make another point, but you really only need 2 points. And then so this part of the graph looks something like this. Okay, now we do the same thing for the orange piece. Start with an x value of -1, plug it in over here for x, and you get -7. So this orange piece starts at -1, -7, and it's only used for x values greater than or equal to -1. Now since it's or equal to, that's why I made this one filled in circle, and this one's an open circle because it was not or equal to. And now you can use your slope here if you want. I'm just going to pick another x value. Anything I can pick anything that's bigger than -1. So I'm going to just choose 0, and I plug in 0 here for x, and I get -4. So I know the point 0, -4 is on the orange graph right here. And then we can draw a line to connect those 2 points. And so we kind of have, two line segments here. Where the orange graph starts here and just goes to the right and up, and the blue graph starts here and goes only this direction. Okay? Now we're going to use the same function from above to evaluate the following. So first I'm going to go through these 4 and figure out which of these I'm going to use based on what x values we're allowed to use, because these are all x values right here. All of those represent an x value. So when x is -3, which is this one, we have to use the blue piece because -3 is less than -1. So I'm just going to highlight this blue so you know that we're using the blue piece. When x is 5, we're going to have to use the orange piece because 5 is greater than or equal to -1. So now we're going to use the orange piece there. F of 0, again, 0 is bigger than -1. So we use the orange piece again. And -1 exactly, which notice is this number, so we use the piece where it says or equal to, which again is the orange piece. Okay, so plug in -3 into the blue piece and you get 2 times -3 plus 1. I'm not actually going to show all this work. Well, maybe I will. All right, so it's 2 times negative 3 plus 1. Let me write that a little cleaner. 2 times negative 3 plus 1, which is negative 5. So f of 3 equals negative 5. That's what that tells us. And then f of 5, I plug into the orange piece, and I get 3 times 5 minus 4, which is 11. 0 gets plugged into the orange piece, so that's equal to 3 times 0 minus 4, which is negative 4. And negative 1 gets plugged into the orange piece. Incidentally, these are numbers we already found when we were making the graph, but I'll still plug it in and get 3 times negative 1 minus 4, and that equals negative 7. Now for these problems, now we know what the y value is because it says when f of x equals 3. So if we know the y value, we have to set each of these equal to 3 because these represent our y values and solve for x. Then we have to check our x values to see if it fits over here. So first let's do the blue one. We have 2x plus 1 is equal to 3. Solve this, so subtract 1. 2x equals 2, and you get x equals 1. Now check that. X equals 1, does that fit in our blue piece? No, because x has to be less than negative 1, and we got an answer that was bigger. So this one doesn't actually work. Let's try it with the orange piece, because it's possible it doesn't work for either. And now we want to do 3x minus 4 equals 3. And you get 3x equals 7, which gives us x equals 7/3. Does 7/3 meet this criteria? Is it bigger than negative 1? And yes, it is. So x equals 7/3 is a solution that works. It's a point on the graph. When x is 7/3, y is 3. That would be a point on the orange graph somewhere. Okay, now we're going to just answer some similar questions using this graph to answer these. F of negative 2, again, these are all x values. When x is this, when x is this, when x is this, when x is that. So when x is negative 2, I'm just coming over here at negative 2 and going up until I find a y value, and I get 4. When x is 0, that's right there, I get 0. When x is 1, which is right here, I get this y value because it's filled in. So that's a y value of 1. Notice how I don't choose this y value because that's not filled in, so that's not actually a y value there. And then f of 2, which is right here, well, same thing. It's not this one because that's a hole. So the y value I want is the y value of this point, which is 3. And then similar stuff down here, except these are all y values. When y is 3, when y is negative 2, when y is 0. So I come and I look when y is 3. So y is 3 is right here. So I have a point here and one right here. So when x is 1 and when x is negative 1. And then now we're going to do when y is negative 2, which is right here, and we have an x value of 5. And now when y is 0, which is here, now this one's weird because it's 0 for all of those numbers, which it's not just negative 5, negative 4, negative 3, and negative 2, because there's infinitely many decimals in between here, like all these infinitely many points. So we can actually write this answer in interval notation. So all x, you can say it like this, all x in negative 5 to negative 2. So that accounts for all this red part right here. All those x values work. But then we also have this one. Remember, we're looking for where y equals 0. So at x equals 3. Okay, and then f of 2, that's me giving you the x value. You would find y. So when x is 2, what's my y value? Well, you might think it's this one, but there is no y value here because it's a hole. So there isn't one, does not exist, no solution, or not a solution, but because we didn't solve anything. But you can just say does not exist or there is no y value there. And that's it for piecewise functions.